Thank you. Hello, everyone. I'm Sorur, PhD student from University of York in England. And today I'm going to present my work titled Partial Loading of Repository-Based Model through a Static Analyzer. Actually, it's part analysis. Actually, it's part of my PhD thesis, which is supervised by Dimitris Kolovos and Simos Grasimo. And it's done in collaboration with Gerson Sonnier from University of Nantes in France. But the whole project, whole my PhD is funded by European Union in the context of Marie Curie program. So today, I'm going to start with problem statement, and then I'll go through motivating example to elaborate a little bit more, and then I'll talk about our approach step by step, and then evaluation and conclusion. Then I will be happy to answer your question if you have any. Okay, as you may know, in MD, models are considered as a main artifact, and these models are input of the programs which called model management program, that are manipulating model, like validating model, transform model, or merging models. The problem that we have faced in this work is about the scalability, which, considering the current technology of MD, when the size of model increase, then the execution engine have problem for handling this such as big models, because when the size increase, the time execution and the memory consumption will be increased, which is not very efficient. Actually, we have two kind of model: the file-based model, when the model is stored in a file like XMI, or when the model is stored in a database, which called repository-based model, like graph-based database or document-based database. But the problem that has happened, like the challenges that execution engine have for handling this big model, is because of the way that this execution engine interact with models. But what I mean by interaction with models, if there is a model which is saved in a file, when execution engine wants to execute the program, first it load the whole model into memory and then execute the program, which is not very efficient, because most of the time there are some information that are loaded in the memory, but they are never used or referenced by the program. So it's like there are some information that are occupied in memory, but they are not used. So it's like wasting the memory. But in terms of repository-based model, there are two strategies: greedy and lazy. It's a little bit better, because in greedy strategy, when the program reference or access to model elements, in greedy strategy, all attributes and references of the model element will be loaded to memory, which is better. But still, if, for example, there is a model element that they have 100 attributes and just three of them are referenced by the program, doesn't make sense to load that attributes which are not referenced by the program. So again, it's considered as wasting memory. In terms of lazy strategy, it's better, because execution engine go through the program, and when it says that, okay, I need this model element, it send request to database, get the information, say, okay, so let's continue the execution. Then say, okay, there is a attribute needed, send the request to database and get the information. So it looked like that execution engine just loading the information that are necessary for executing the program, which is good, which is efficient. But in terms of time, it doesn't make sense, because multiple round trip to database is taking time, which is, again, in terms of time, doesn't consider as an efficient thing. So our idea here is partial loading. It means that if we can analyze the program and we understand that which part of model is necessary for executing the program, then we can just load that part of model and execute the program. In this way, we just occupy the memory by the necessary information, and we just do it in one go. Then we don't have multiple trips to the database. So maybe by motivating example, it's more clear that what I mean. Here we have a meta model. There is a project class here. This project is done by some task. This task can be automatic or can be manual. If the task is manual, then it needs some effort to be completed, and these efforts are making by some people, right? And here we have a EOL program. EOL program is this language that we are using for writing this program is Epsilon object language. This is a part of Epsilon language, and Epsilon is like family of languages for manipulating model, like a specific task-specific languages, like for validating, for merging, for whatever. In this program, which is like a simple program, we are going through the all instance of manual task in the model and try to first print the title of the task, and then see that how many people are like making effort to completing this task, right? So it's very like simple program. But if the model is stored in a database, how the lazy strategy is working here? The execution engine say that, okay, there is a manual task at all instances, so we need all instances of manual task. It send a request to database and get the IDs of all instances of manual task. After that, they say, okay, for the specific ID, I need the title. Send another request and get the title for that specific ID. In the next line, the effort reference is needed. So send a request, get the effort. And next, there is a person reference which is needed. And again, send the ID and get it. So consider that if we have very big model, like million of elements, how many time it should access to database and get data back, right? So it look like there is a lot of time spending here for loading this information from database. But what is our idea saying is, first, analyze the program and understand, okay, we need all instances of manual task. From this manual task, we need title, just title attribute, and just effort reference. And from the class of reference, we need the person reference, not other references, not another attributes, just these two. So we send a request to database and say that, see, I need manual task, I need ID, I need title, I need reference, and get it back in one go. So in this way, we are loading our information that we need for executing the program, and then we can execute it in an efficient way. So this is the overview of my approach, that's how we can do it, how we can analyze the program, how we can send a request to database and get it back in one go. I will go through this overview step by step, then maybe it's easier to understand. First step is static analyzer. As Gorat mentioned, because we implement this static analyzer as a part of our PhD in collaboration with each other from University of York. So in a static analyzer, the role of a static analyzer is to analyze the program, and from the AST, abstract syntax tree, create an abstract syntax graph. It means that just set the result type. So considering the program that we mentioned, manual task at all instances is an operation call. But in a with static analysis, we say, okay, task is a model element. What's the type of this model element? It's manual task. Or here we have operation call. Okay, there is an operation which is called here. What's the result type of this operation? It's a sequence of manual tasks. So by static analysis, we have an idea that what's the result type of each expression here in the program. Using this information, then we can extract effective metamodel. We design and implement an algorithm for extracting effective metamodel from static analyzer. Effective metamodel is the subset of original metamodel, which consists of just the information that are necessary for executing the program. So if you compare the original metamodel, which consists of all information about the model. In effective metamodel, we just have idea about that which part of model is necessary for executing the program. For example, here we say, okay, there is a manual task, all instances. All instances means all of kind. So we add manual task and a reference of all of kind to our effective metamodel. So you're looking at effective metamodel, we understand that we need all of kind of manual task. After that, here we say, okay, task that title. It means that title of task is needed as well. So we add it to our effective metamodel. And then reference, effort reference of task, and person reference of effort. So this is the whole information that we need from the model for executing the program. So if we load model based on this effective metamodel, then it will be more efficient, because instead of loading based on original metamodel, we are loading based on effective metamodel. So we just load the information that we need. But how we can do it? In this work, because the state of arts, like the repositories like NeoEMF, that is like a mature repository in MD or CDO, all of them are considered graph-based databases because mapping model to graph is easier and it makes more sense. So we in our work we consider Neo4j as well as a backup, like as a database which store our models. So here, how we in this figure, you can see that how we map the model to a graph. For each class in the model, we have a node in the graph, and we set the properties of each node based on the attribute of the class. And for the reference between two classes, between two instances of classes, we add the age between two nodes. So in this way, we are mapping the model to like graph nodes. And we label nodes as a type of the class and the superclass. For example, here, the manual task node is labeled as manual task and task because it's efficient. It's better for creating query that we need. But because we need to know that what's the exact type of this node, we add another node with the instance of age, and then through that age, we can understand what's the exact type. Okay, so now we map the model to a graph. The graph is in Neo4j database. It's stored here. On the other hand, we have effective meta model. We know that we need this kind of information. But how we can load information from the database using the effective meta model? Obviously, because we are considering Neo4j database, we need Cypher queries. Cypher is a language for querying the Neo4j database. So the idea is we can translate this effective meta model to Cypher queries and then load the information that we need from the Neo4j database. How we can do it? How we can translate effective meta model to Cypher queries? Here, I mentioned some expression of Cypher. For example, the first one is match. When we say match X, like X is a label of node, it means that load all node with this specific label. Or for example, when we say optional match in Cypher expression, then it's like defining a pattern to following the node. Here we can see that there is a source node, and then there is an edge and target node, and with optional match, it's return the target node to us. And return is just for the property of the node. So when we have effective meta model like this, when we look at all of kind, so we think that, okay, it means that we need all nodes that have manual task labels. So we use match with the label that we need, right? After that, attribute is needed. So we say that, okay, please find the nodes that have this label and return just the title, just one attribute that we need, not other attribute, right? So return a title for us. After that, we say, okay, there is a reference here as well. As I mentioned, for reference for pattern, we use optional match. So optional match, we say, okay, from the task, there is effort, and then there is an effort like as a target node, we need the ID of that effort, right? And at the end, there is a person reference. Again, we use optional match to following the pattern and find the person node. And as you can see, because there is no attribute here that we need, just we return ID, and it's like enough for executing our program. As we saw in the last slide, we generate the query based on effective meta model. But we don't need just to generate query. We need the query that is optimized. The query, because if we want to consider this query, it's 3 times access to a database and return this, return this, return this. So it's like the lazy strategy that we say it's not a very good idea to access multiple times. Here we use some query optimization, like we use label, we use some techniques to avoid Cartesian product, we try to reduce the cardinality. All of these techniques are mentioned in the paper. So please, if you are interested, just look at paper because it's too much detail if I want to discuss it here. But at the end, the query that is generated in this way will be transferred to the query like this, which is like one query. So you can see that in one query, we can load all information that we need based on the effective meta model. Okay, so we analyze the program, we extract effective metamodel. From the effective metamodel, we generate query, and using the generated queries, we load the information from the database, and then using that information, the execution engine can execute the program, and we expect that this output will be generated in a more efficient way in terms of memory and in terms of time. So for evaluation, we use a Grabat case study. Grabat is some Java model which are reverse engineered from the Java project. There are five sets of models. There, the minimum is about 70K model elements, and it go to 5 million elements. So we run the Grabat query and use multiple, like 5 models, and try to measure the time and memory. As I mentioned earlier, we compare our work with NeoEMF because NeoEMF is a state of art and it's like a mature one in MD right now. So as you can see, just in the first one, the NeoEMF, it has a better time because the number of elements are not that much, so it couldn't like pay the overhead for the static analyzer for generating queries and this stuff. But after that, as much as the number of elements are increasing, the time is better, and our approach perform better compared to NeoEMF. So as a conclusion, I presented the approach to loading the model from repository-based model, specifically Neo4j database, partially. And as you see that in evaluation, we saw that the time and memory consumption reduced. But the interesting idea for the future work is, okay, we say let's load the information that are necessary, that are needed in one go, and then, but maybe it happened that the memory even is not enough to accommodate the necessary part of model. Then what will happen? So for the future work, we are thinking about partitioning this kind of information. Like, okay, there are the necessary information that we need to load, but instead of loading them in one go, partition them first. Load the first partition, execute the program, then when these information are not referenced by the program anymore, dispose them, and then load the second part. So in this way, maybe the time increase, but at least we can, like the program will be executed, which is like right now will be failed to execute, right? Because model is very big. Thank you very much for your attention. This is my email address. If you want to see the code, it's available in GitHub and my LinkedIn profile. If you have any question, if you have any idea, if you want to discuss, please feel free to contact me. Thank you.
Thank you very much.
So in the evaluation, you include the time for the static analysis in the time shown?
Yeah, it's like end-to-end.
Okay.
From the static analysis, generating queries, accessing everything, yeah.
Okay. Any other question about the email?
Why did you decide to use Neo4j? I understand that it's Cypher, because in the past I thought about using Cypher, and in the end I decided to use SEP, the complex web processing. It's linear, I know it's not the same, but I found Cypher kind of slow sometimes, at least when querying large graphs. So did you try another way, or what was your reason to choose that one?
Yeah, first, actually, I tried to build this work on top of NeoEMF because NeoEMF are already supporting lazy, greedy. So I could say, okay, let's add the partially. But, and Jeff Sonsoni, that is like main developer of NeoEMF, is part of this project because I contact him and talk to him about this. But then we realized that the fundamental doesn't allow us to add this because they use some like Java APIs, and with that you can just ask for a single attribute. But in my approach, I need something to ask for some attributes, some references, and then we were thinking that maybe Cypher is very slow. But when we check and like first we check just the Cypher, not in our approach, just generate some queries and try to benchmarking and see the time and compare. And I see that because I got this comment before that be careful, Cypher is very slow. But when we check, we saw that if we optimize the query, it's worked very well. So that's why I add that tree optimization, and then when we compare, we saw that it's working. Yeah. So first we tried that, but then we switched to Cypher because Cypher is the only way to, like the query language for Node for Java Cypher. Yeah. So thank you.
Okay. Thank you very much.
Thank you.